are not so commonly used. Because, okay, so in the X representation, the propagator is some horrible Hankel function, and you have to integrate, say, product of Hankel functions over 4 arguments. So that's a horrible task. And so the propagator looks much easier in the momentum representation. So the idea is that we just transform all our Feynman rules into momentum space. And so then this would simplify life a little bit just because we will need to integrate rational functions. So let's see how does it work. How does it work? So first of all, this is, of course, is the integral. Let me write it this way. So it's I g squared minus m squared. And then I have e to the minus ipx times e to the plus ipy. So this is just a funny way to write a single exponential, okay? Because this is e to the ipx minus y. The reason I want to write it this way is that then I can assign the exponential factors to the endpoints. So I say that I have a propagator connecting points x and y, and I assign a momentum flowing through this propagator. Actually, it's convenient to think of this propagator as a trajectory of a particle that connects x and y. And so p is the momentum of this particle. So from this formula, I see that I should assign the wave function e to the minus ipx to the incoming point, and the wave function and the conjugate wave function for the point in which, to the endpoint of the propagator, and then an overall factor of e squared of I divided by p squared minus m squared to the line itself. So this endpoints in the Feynman diagram, in some Feynman diagram, these endpoints can be either external point or a vertex over which we then integrate. So let's look what happens at the vertex. So we have a vertex at the position x. And now let's assume that all momenta that flow into this vertex are incoming. Well, that's not a restriction really, because we can redefine the direction of this momentum. So if we flip the arrow, this means that we just flip the signs here and there. So we can always assume that these momenta are all incoming. So this gives us, so the vertex itself gives a factor of minus I lambda and then d for x. And then we should take the product of the wave functions. So this would be Ix, and then the sum of the momentum. Now x doesn't appear anywhere in the diagram now, because you see we disentangled, this way we disentangled the x dependence in the propagator. So this is the only place where x appears, so we just take this integral. This gives us minus I lambda times 2 pi to the 4, and then delta of pi 1 plus pi 2 plus pi 3 plus pi 4. So this is just momentum conservation. So the total momentum inflowing into this vertex should be 0. And so the momentum space Feynman rules are thus pretty simple. So we associate, so we should draw a diagram, assign momenta to all internal lines, taking into account momentum conservation. So momentum, it's like using Kirchhoff rules for electric networks. So the momentum should be always conserved. And then each propagator gives you a factor of I divided by p squared divided by m squared. And each vertex just gives a factor of minus I lambda. So let's do an example to see how it all works. So as an example, let's consider a second order correction to the propagator. We'll only discuss one diagram. It's sometimes called the sunset diagram. So we have two external points. X1 and X2. And then we have this double bubble in the middle. So then we start assigning momenta to all the lines in the diagram. So here we have, say, momentum P. And then, so this momentum branches into three momenta there. So let's say that this momentum is K. This momentum is Q. And this momentum is, well, this momentum we know, because there is a conservation of momentum in this vertex. So the momentum going here must be equal to P minus K minus Q. So that at this vertex, the momentum is conserved. Now you see that at this vertex, the momentum conservation then unambiguously determines the momentum over there. And, well, the momentum flowing through the whole diagram, is just given. It's just one momentum, not the two. So then we start writing the analytic expression for this diagram. So each vertex gives a factor of minus I lambda. There are two vertices. Therefore, this appears squared. Then we need to divide by the symmetry factor. So this is equal to 6. It's the group of permutation of these three lines. You see that they're all symmetric. And so the order of group of permutation of three objects is equal to 6. And then we just, well, so you see that there are two momenta that are undetermined. K and Q are, well, just hold on. So there will be, so each momentum should be integrated over. So integration over the momentum flowing through the diagram just gives the Fourier transform of the of the distance. So in the diagram, and then the interesting, well, part appears here. So there is also there are also two propagators with this momentum. So there is a factor of I divided by p squared minus m squared. And then there will be an integral over two momenta k and q. And we should multiply all propagators that appear here. So now this just gives the Fourier transform. And so the correction to the propagator is this. So this would be a two-loop correction to the Fourier image of the propagator. So why two-loop? Well, you see that there are two closed contours here. Just a second. And each of the contours is associated to its momentum. So there are two momentum integrations. So the number of momentum integrations is equal to the number of closed loops in the diagram. And also the factor of lambda grows with the number of loops. So to really find this correction, we would need to complete this integral over q and k. Yes?
When we were talking about the position space rules, then we said that we associate with each internal vertex one of the integration factors. Is that still the case here? I'm wondering what parts of the diagram the three integration factors come from.
So you see, in the momentum space integration, we already have done integrations over positions of the vertices. So the x integration just produced the delta function that represents momentum conservation.
Sorry, and then each of these integrals in this final mathematical expression, each of those comes from, instead of coming from one of the internal vertices, now it comes from one of the momentum that was originally drawn in the diagram.
That's right. So that's right. So draw, so the idea is following. So you assign momenta to the propagators in such a way that the total momentum, in such a way that momentum at each vertex is conserved. And then there will be some undetermined momenta here. And so you have to integrate over all undetermined momenta in the diagram. So in this case, we have 1, 2, 3 undetermined momenta. Now, it turns out that the momentum that flows through the whole diagram is just Fourier variable dual to the position of the endpoints. So really, there are only two interesting integrals, or two integrals that we really need to calculate. Yes?
Sorry, if we're considering this a correction to dp, shouldn't we include the lambda factor in the correction?
Yes, absolutely. So this, yes, so this would be the full correction. So there was another question. Yes.
So, assuming that if we wanted to n order correction, we need to have n corrections.
Yes. Now, there is a simple physical interpretation of the diagrams. You can think of each of the lines as representing a particle. So what happens here is that this external source, so we are computing the two-point function of two fields, right? So each field is a source of one particle. So it creates a particle in point x that propagates with momentum p. And then it decays into three particles. So, but particle, it decays in such a way that the momentum, its form momentum is conserved. So two of these particles have momentum k and q, and then the momentum of the third particle is determined. Then these three particles, they undergo another interaction so that they produce this particle that is absorbed at x2. So the whole picture can be thought of as representing some process of interaction between particles. And that's a very useful way of thinking about Feynman diagrams. You can really imagine that they represent some space-time processes of particles colliding and annihilating, etc. Yes?
Wait. We say that the internal particles are off-shelled often, don't we? I mean,
Yes.
it's like you can mathematically could get a negative p0 in one of the intermediate steps.
Absolutely. Yes. So they're called virtual particles. They're off-shell, indeed. So we integrate over the whole form momentum, not imposing the condition that p squared is equal to m squared. Okay, so that's it for today. And tomorrow we will study how to calculate some real physical processes using Feynman rules. Yes?
I think I was reading on the PI faculty page at some point that someone has created a method to compute infinite loop Feynman diagram.
Sorry?
Someone has created a method to compute infinite loop Feynman diagram.
Oh, yes, this is that's right. So it's a big subject here that people are working on the methods to efficiently compute. You see, these integrals are very complicated.
Yeah.
They become complicated when you take corrections of higher and higher orders. And I mean, although these techniques are 50 years old, there is still something one can do to improve this, the methods. So it's, yeah, it's, in particular, people in PI are working on that. Yes?
What is the difference between the element of the diagram that is associated with an integral over, let's say, d4t, and the element in the diagram that is associated with an I over p squared minus m squared. Which element of the diagram is mapped to each of those mathematical equations?
So each propagator gives a factor of I over pi squared minus m squared. So you see that these two propagators are mapped to this factor. This propagator is mapped to that factor. And so that's the only element. In fact, the rest is just the integration. And you integrate over all momenta that appear. Now, the only way to learn it is just to calculate one diagram yourself, and then you will know how to do it. So thank you for your attention. That's it for today.